Welcome to Geometry Topology Today. I'm Shea Velovic, a mathematician at Louisiana State University. We're here talking with Clayton Shonkwiler, who's a professor at Colorado State University, and he's going to be telling us a little bit more about random polygons, but now from a slightly more advanced perspective. So, welcome.
Thank you.
And why don't you tell us a little bit more about this problem?
Yeah, so in the previous video, I introduced this question of what's the likelihood that a random triangle is obtuse? And so I said what the answer was. It's about an 84% chance that a random triangle is obtuse. But now maybe we can go in a little bit more of the details of how to work through that problem.
Sounds great.
OK, so if you're interested in whether a triangle is obtuse, the real question is you just care about the shape of the triangle. So you don't care about its location or its orientation. It's just sort of the shape is the most important factor. So let's see how to deal with that issue. So if I have a triangle, let's say like this, and it has edges E1, E2, and E3. Now, one easy way to make the problem sort of translation invariant is to think of these edges as vectors.
As opposed to thinking about the vertices of the triangle, the points
for
in
example.
the plane.
Yeah, exactly. So thinking of these as vectors now makes this a translation invariant problem. So that's the first trick. The second trick is to think of these vectors equivalently as complex numbers. They're vectors in the plane, so you can think of them as complex numbers. And then the magical thing to do is to think of square roots of these complex numbers. So now I'm thinking of E1, E2, and E3 as the squares of complex numbers Z1, Z2, and Z3.
OK.
So notice, first of all, that there's sort of two choices for what Z1 could be. It could be either Z1 or minus Z1. And so you have two cube total choices for sort of taking these square roots. So that's something to keep in the back of your mind.
So we should see 8 copies of something.
Exactly, exactly. So now you have these three complex numbers, Z1, Z2, Z3. You can package them into a vector, Z1, Z2, and Z3. Now, of course, Z1, Z2, and Z3, if we write them out as the real and imaginary parts, they look like this: A1 plus B1i, A2 plus B2i, and A3 plus B3i.
So thinking about C3 as R3 squared.
Yeah, exactly. And so, in fact, we can think of these now as, OK, I have a vector of the A's. I have a vector of the B's times I. And so now I've turned my triangle into a pair of three-dimensional real vectors, A and B.
But now we have to figure out what makes it a triangle.
Yeah, exactly. So if I just took three arbitrary complex numbers, Z1, Z2, Z3, and then I squared them and then thought of those as vectors, well, in general, your three vectors wouldn't form a triangle. They just form sort of,
some linkage that goes wherever.
Exactly. So what's the condition that it's actually a triangle? Well, you say that you have to get back to your starting point,
right,
which means, thinking of these again as vectors, that the vector sum of the three edges has to be 0. So if you think of that in terms of the z's, that tells you that z1 squared, which is edge 1, plus z2 squared, which is edge 2, plus z3 squared, which is edge 3, has to be equal to 0.
That's clear enough.
Yeah, so that's the condition. And now you can ask, well, what does that mean in terms of my real part and imaginary part? So this is pretty much just a calculation. So what does the calculation tell you? Well, it tells you that this condition is the same as the condition that the norm of A as a three-dimensional vector is equal to the norm of B as a three-dimensional vector, and that the dot product of A and B is equal to 0, So the condition that you have a triangle is that these vectors of real and imaginary parts have the same length and are perpendicular.
I see.
So, OK, you've now succeeded in turning one problem into a slightly different problem. What was the point of that whole business? Well, the point is that now collections of vectors like this form a really nice space called a Stiefel manifold. So what I'm going to do is I'm going to fix the scale. So I'm going to fix that the norm of A is equal to 1. And this turns out to be equivalent to saying that the perimeter of the triangle is equal to 2.
So this is somehow like a scale invariance.
Yeah, so again, if all I care about is it obtuse or acute, well, that's a scale invariant kind of a situation, so I might as well just pick a particular scale, and my scale is going to be that the total perimeter of the triangle is equal to 2.
So as long as two triangles are similar, they sort of count the same in whatever this space is you're working in.
Exactly. So then what this tells you is that triangles up to translation and similarity correspond exactly to a manifold that I'm going to call V2, R3. And so this is what's called a Stiefel manifold, and it consists of pairs of perpendicular unit vectors. So the pair A comma B gives you the Stiefel manifold V2, R3.
So exactly this condition.
Yeah, exactly. OK, so how to think about this geometrically? Well, the way to think about this geometrically is that this corresponds really to the two-sphere. Just the round two-sphere, yeah.
How do you see that?
OK, so if you have a pair of perpendicular unit vectors, again, think of them as A and B, well, how do you get a point on the two-sphere? Well, you just take the vector that's perpendicular to both.
So the cross product.
So you just take the cross product, exactly. So if I take A cross B, now that's an element of the two-sphere, and so that's a point on the two-sphere that encodes the triangle that I was interested in to begin with.
So the space of triangles in R3 is the two-sphere.
Yeah, so now I'm going to draw the space of triangles in R3 as the two-sphere.
So which ones are obtuse?
Well, so now, getting back to the question, which ones are obtuse? Well, it's really useful to think about, you have acute triangles, you have obtuse triangles, and if you think of those as sort of two countries in the space of possible triangles, what's at the border between those two countries? Of course, it's the right triangles, right? So, OK, so then if we can figure out what that borderland is, we can get a good handle on what these spaces actually are. And so it turns out that the border between these two things, well, it's the right triangles. How do you recognize right triangles?
Well, in terms of angles up here, or lengths via the Pythagorean theorem?
Yeah, so for example, you could say, well, you're a right triangle if, so it's actually the sort of the converse of the Pythagorean theorem, says that you have a right triangle. Really, so the Pythagorean theorem is really an if and only if kind of a statement. If and only if the length of E1 squared plus the length of E2 squared is equal to the length of E3 squared. Or, of course, you could cyclically permute. It could be that, well,
depending on where
E1 is the hypotenuse, so it's E2 squared plus E3 squared equals E1 squared, and so on.
I see, and this is this eightfold symmetry.
Yeah, again, you're seeing this sort of symmetry again. So now if you translate this condition onto the sphere, so if I think of this now as a point x, y, z, just because we like to write points on the sphere in x, y, and z coordinates, then this condition turns out to be the same. So the right triangles look like, z squared equals x squared times y squared, or y squared equals z squared times x squared, or x squared equals y squared times z squared.
And this is something you could feed into a computer and get some beautiful
Absolutely,
picture.
yeah. You have to write down, well, what's the formula for the cross product, and and you sort of go from there. And so what this actually looks like on the sphere, well, here's, again, you have this eightfold symmetry, so really you're going to see 8 copies of the thing that I'm very poorly drawing. This is just sort of a long, skinny neck here. And so these 3 curves together are sort of these 3 curves. And again, because of the squares, of course, you could have minus z or z, and it's the same sort of thing. And so what you get out of all of this is that the right triangles are these sort of funny-looking triangles on the sphere.
It's kind of like a hyperbolic triangle in the round 2 sphere.
Yeah. It's actually not, but it looks like that, yeah. And so then the question is, well, and again, there's 7 more of these, sort of, 4 in the northern hemisphere, 4 in the southern hemisphere. And then the question of, well, what's the likelihood of being acute is the question of what's the area, if you fill these shapes in, what's the area of these 8 shapes?
So these guys here are the acute ones, and then the complement is the obtuse?
Exactly. And so how do you compute the area? Well, you're integrating the area form on the sphere over these regions. And you can use Stokes' theorem to turn that into a line integral on the boundary. Now, of course, because of the symmetry, you really just have to compute one line integral for one of these curves. And then whatever answer you get, you multiply by 24 because there's 24 of these total curves. And so then the answer that you get, in fact, is, let's see, where should I write this? The answer that I get should be the probability of being obtuse is equal to 3 over 2 minus the natural log of 8 over pi, which is approximately 0.838.
That's wonderful. All right. So maybe let's take a break for a moment to erase, and then you can tell us a little bit more about generalizations of this problem.
Sure, absolutely.
Welcome back. We're here with a clean board, and Clay's now going to tell us a little bit about some generalizations of this triangle problem.
Yeah, so, well, first off, let me, in talking about these triangles, we brought up the Stiefel manifold V2R3, which is perpendicular vectors, pairs of perpendicular unit vectors in R3. And basically the same story that I told before allows you to generalize to V2Rn, which now you're going to think of as corresponding to n-gons in the plane.
So this is sequences of edges where eventually you come back where you started.
Exactly. And so the condition that these two vectors are perpendicular and the same length is, again, exactly the closing condition for these n-gons.
But here where you say n-gons, these things may cross themselves, or
exactly,
it's not going to necessarily be like a triangle where it
right, so
convex.
Triangles, you know that it's always going to be convex, but in general, even for quadrilaterals, you can have non-convex things, you can have things that self-intersect, and that's all sort of allowed in this theory. And so, okay, so these are n-gons in the plane, but there's another symmetry that we sort of haven't dealt with yet, which is that, well, again, if you only care about the shapes, you might as well divide by the rotations of the plane, and in fact, also the reflections of the plane.
I see. So we had been implicitly talking about this when we were mentioning similarity of triangles.
Yeah, exactly. So it's, of course, if you want to divide by rotations and reflections, that's the group O2, which acts on the plane. It also acts on this space. So if we think of these, these are pairs of orthonormal n vectors. So if I think of that as an n by 2 matrix, so a tall, skinny matrix, then I can multiply by a 2 by 2 matrix on the right and get a new tall, skinny matrix. And what that does in terms of these vectors is you have these perpendicular vectors, and you're just rotating within the plane that they span if you multiply by an O2, or you're reflecting in the plane that they span. So when you take the quotient by this O2 action, you get a very famous manifold called a Grassmann manifold. So the Grassmannian of two planes in Rn, so these are now just planes, two-dimensional planes in n-dimensional space. And it's clear that that's the quotient, because if you have these frames and then you're dividing by all possible rotations and reflections of the frames, then you're saying, well, you're sort of identifying all possible orthonormal bases of a particular plane.
I see. And since we used O2 instead of SO2, including the reflections, these would be unoriented planes.
Exactly, yes. Now it turns out that this O2 action, when you descend to the level of n-gons, is again the O2 action on n-gons. You're just rotating the n-gons. Because of the squaring that we had before, you're rotating twice as fast, but it's still just a rotation.
Okay.
So in fact, these guys are n-gons in the plane, up to rotation. So now you've sort of divided by rotations, and you're really just looking at the shapes as opposed to orientation or location or whatever. So that's one generalization, is just to n-gons in the plane. Then you can ask questions about, like, what's the sort of average shape of an n-gon? What's the diameter of it? What's the probability that it's concave or convex?
So all of these geometric properties that you care about for polygons, you could sort of ask those same sorts of questions in this setup.
Yeah, and this space is wonderful because this is such a beautiful space. It's a Riemannian manifold. It has a transitive ON action because these are planes in Rn. Of course, ON acts on Rn. That actions by isometry, so this is a homogeneous space. It inherits a nice Riemannian metric from ON, which is a beautiful Lie group, has a bi-invariant metric.
So it's the nicest possible space you could imagine.
Yeah, it's absolutely wonderful. It's so all these questions you get asked about n-gons in the plane, you just translate them to this language, and then you have all these geometric tools to try to answer those questions. And in fact, you can make a lot of progress in answering those questions because you understand this space so well.
So are there other generalizations?
Yeah, so what else can you do? Well, n-gons in the plane are great, but in the first talk, I promised a connection to polymers. And
I see, and polymers live in 3 space.
And polymers live in 3 space. Like you can do things where you sort of pin them to planes, but generally speaking, if you're thinking about the DNA in your body, it's in 3-dimensional space, not in a 2-dimensional space. And it turns out that the exact same story works, where now instead of so thinking of the edges as complex numbers, what you're basically going to do is think of the edges as being modeled by quaternions. And you can think of a quaternion as a pair of complex numbers. And so instead of pairs of real vectors, you get pairs of complex vectors, again, that are perpendicular in unit length. Those are the conditions that ensure that whatever your weird polygon is gets back to the starting point.
Right.
So this is the Stiefel manifold of 2 frames in Cn.
And then we want to mod out by rotations and
exactly. So now rotations of R3 is the group SO3.
Right.
Well, of course, SO3 doesn't exactly act on this space, but a group that does act on this space is U2. Again, thinking of these as tall, skinny matrices, you multiply on the right by these 2 by 2 matrices. All you're doing is you're taking these complex vectors and rotating them within the complex 2 plane that they span. And of course, U2 is a circle bundle over SO3, and so it turns out that U2 action descends to the SO3 action on n-gons. So let me say these are now n-gons in R3.
So again, sort of sequences of steps where you're required to close up at the very end.
Exactly. And then when you take the quotient of the Stiefel manifold by the unitary group, you get the Grossman manifold G2Cn.
Which also has all of these nice, beautiful
And
properties.
even more, because now this is a complex manifold, right? And so you can think of it in sort of complex geometry. You can think of it in symplectic geometry. So you have even sort of more structure than you had in this story.
Oh, that's wonderful.
When you're here. And because it's also a projective variety, right? You can now start using complex algebraic geometry to think about this space. Whereas here, I mean, it's a real projective variety, but of course, real algebraic geometry is sort of much less well understood than complex algebraic geometry.
So you could start trying to tie all of these wonderful characteristics that you know about this space to the linkages that they represent.
Right. Exactly.
Okay, so what's the connection to polymers? And what is a polymer?
Okay, so, well, I described a little bit what a polymer is in the previous video, but a polymer, the way to think about it is it's just a long, stringy molecule, basically. Of course, it goes on and on.
And maybe it doesn't have curved edges.
And then maybe it doesn't have curved edges. So, but abstractly, you should just think of a polymer, it's sort of a sequence of monomers bonded together in some way. And you think of the monomers as more or less being identical, even though, maybe they're base pairs, maybe they're amino acids, so maybe they're not exactly the same. But you have these long, stringy molecules. And they are quite flexible because they're very long. And so sort of the idealized model of them is as a random walk. So a random walk just meaning, you choose a starting point, you choose a direction uniformly on the possible directions, you take a step in that direction, and then you iterate. You're at a new point, you choose a direction, you take a step, and you keep going. And so random walks have been sort of the model, the super idealized model of polymers for 40 or 50 years. But then, well, random walks are kind of easy because the steps are independent, but if you're interested in what are called ring polymers, so examples are like plasmids or like viral DNA, so polymers that have to close up and form a loop, then you've killed the independence of your step directions in your random walk. So now you're talking about a random walk that's constrained to close up and form a loop.
And I imagine that's a much harder problem.
Yeah, absolutely. Because now you're not talking about independent random variates, you're talking about sort of joint distributions, multivariate joint distributions of random variates.
I see. And in such a situation, it would be great if you knew that all of these linkages were represented by some space like the Grassmannian, where you could work in that space instead of trying to figure out what all this dependence is.
Yeah, so instead of sort of trying to understand the joint probability distribution from sort of a very hands-on perspective, if you can see it as, oh, well, this joint probability distribution comes from Haar measure, for example, on this beautiful, beautiful space where you have, Riemannian geometry, symplectic geometry, algebraic geometry, all these tools that you can use, then you can start doing things like say, okay, well, if you're a polymer physicist, one of the very few things you can actually measure about polymers is a quantity called the radius of gyration, which is, the way to think about it is, the definition is it's like sort of the mean squared distance to the center of mass.
So this is something kind of like a diameter.
It's kind of like a diameter. So you can kind of think of it as like the radius of a sphere with, similar sort of momentum properties as the actual object. And so, but it turns out that you can turn this computation about like what's the average radius of gyration for a closed loop random walk, and that's just an integral on this manifold, and you can evaluate that integral and get it, get the answer, and then you know what it is. And so the polymer people are really interested in this because in polymers, one of the big things is creating new polymers with new material properties. And one of the ideas of how to do that is to create polymers with like different topologies, not strands, not just loops, but like forming more complicated, say, multigraphs.
So different topology might mean some submanifold or subspace of the Grassmann manifold.
Or a product of Grassmann manifolds, or some sort of combination in some interesting way of Grassmann manifolds, right? So, one silly example is, well, if you take a polymer loop and then you put a tail on it, so these are called tadpole polymers. And so you can think of this is like a product of a Grassmannian for the loop, and then this string is like just a random walk, so your moduli space of sort of unconstrained random walks. And so this is like a product space, and then again you can answer these kinds of questions. And so what you can do is you can, okay, this quickly becomes a computational problem rather than a theoretical problem,
right?
Because in practice, a lot of the integrals you want to compute, you can't compute analytically. What you're going to do is you're going to compute them by Monte Carlo integration. And so what you really want to do is you have some moduli space, you come up with a really good sampling algorithm.
And you hope that your space is well adapted to this.
Exactly, exactly. And so for these spaces it is. You can come up with linear time perfect samplers for these spaces, and so you can do Monte Carlo integration really, really fast. And then what people are doing is, okay, we're trying to create these new polymers with these new material properties. How do you identify what you have? Like you have some chemical reaction, you don't get 100% yield, you get various other things that you actually didn't want.
So you might know that there are 6 possible polymers that pop out of some particular chemical reaction,
right.
And you want to know how do I tease out number 1?
Yeah, exactly. So for example, the Tezuka lab in Tokyo recently synthesized a K33, the complete bipartite graph on 3 things and 3 things. And it's amazing what they did. But in fact, to identify that we have a K33, they use numerical simulations based on this Grassmann model of these things to say, oh, well, we expect the radius of gyration to be this. Well, actually, I think maybe it was the sedimentation coefficient, which is related. They said, we expect it to be this for the K33, and it should be different for the other outputs of this reaction, and we can sort of isolate the K33s from the other things.
I see. So that's sort of like marrying the polymer science in a concrete way with the theoretical mathematics.
Yeah, and you're using all these tools from theoretical math to do exactly this kind of problem of identifying new synthetic polymers. It's really, really cool.
All right. So what sort of things need to be incorporated into this theory to take it further?
Yeah, so a big thing is actual polymers. Like you can't pass them through themselves. I
see. So you couldn't have a polymer that sort of lies on top of itself.
That lies on top of itself. Or you can't have a situation where 2 vertices intersect or 2 edges intersect. And so a big question is, well, how do you incorporate those things into this framework?
So you need some sort of exclusion properties or some
Yeah,
ways
so
of
this-
recognizing that naturally in this space.
Yeah, so this is what's called excluded volume. How do you incorporate excluded volume into the theory? So just one example of how that could work is, well, if you have your random walk and you come back to the starting point too early, that's like having a little polygon inside of your bigger polygon.
Right?
And so, okay, well, if polygons are Grassmannians, that's like having a little Grassmannian inside of your bigger Grassmannian.
And then if you kept going, that would be another little Grassmannian.
Yeah, so that would be another little Grassmannian. So what you have is like a product of little Grassmannians inside of the big Grassmannian. And okay, well, in practice, of course, two vertices aren't ever actually going to intersect, but they come within some epsilon of each other, and you want to exclude that. You really want these vertices to stay sort of away from each other.
I see. So you have products of Grassmannians sitting inside of Grassmannians. Those are the where things come together, and you want to remove some sort of sensible neighborhood of these.
Exactly. You want to remove some like tubular neighborhood, and then understand the complement of this tubular neighborhood, the geometry of that. So incorporating these excluded volume constraints is a really important sort of next step. Incorporating other topologies, not just these loops, but like these complete bipartite graphs or theta curves or various other sort of topologies that your polymer might take. If it's a branching polymer instead of just sort of a nice linear polymer, how do you incorporate that into the theory? Yeah.
Oh, wonderful. So I guess maybe one last question would be, if you were giving advice to a graduate student or a researcher in a different field about ways to learn more about your work or places to get started, what would you say?
So I would say that, the really important thing is just how can we, use tools from the geometry to answer these sort of applied questions, these polymer questions. So learning about homogeneous spaces. So seeing this as a homogeneous space with this transitive action, that's what gives you the Riemannian metric. That's what gives you the nice measure. And whether that would be in like a Lie groups class or like a Riemannian geometry class, learning about homogeneous spaces and Grassmannians. I think one of the really important things for the future is using the algebraic geometry to try to answer some of these questions. So again, I said this is a projective variety. So far that hasn't really been used, but I think it's sort of a gold mine for sort of future applications of this theory is using the algebraic geometry. And also, I haven't really talked about the symplectic geometry, but again, sort of getting sort of some entree into the symplectic geometry is sort of a good thing to do. And also just because for pure mathematicians, it's a little bit hard to apply these things to these actual problems without having some knowledge of probability theory and measure theory. And things like, well, how do you cook up good Markov chains to sample this space? So some of that stuff too really comes into the story and is really important.
Wonderful. Well, thank you so much for coming.
Absolutely.
Really appreciate it.
Thanks.
And thank you for watching.